Welcome to Pilot Training Solutions. Whether this is your first step in passing your aviation written exam or one more attempt out of many steps to finally complete it, Pilot Training Solutions can assure you that it will be your last. Now let's be honest. None of us got into aviation because we wanted to take a written test. So why should we spend any more time or energy than absolutely necessary to put this obligatory step behind us? That's what Pilot Training Solutions was created for, to provide a solution to this very present pilot training problem. The genius and success of our programs is attributed to the efforts and experience of one of the most talented CFIs in the industry, Lucas Noya. With over 20,000 hours of teaching in the airplane and in the classroom under his belt, Lucas has provided training solutions to hundreds of students just like you. The easy practices presented in this course were developed by him over several years of hands-on teaching. Lucas recognized that the single biggest factor affecting a student's inability to complete their flight training was passing the written exam. Less than a quarter of those who begin flight training will ever even attempt the FAA's knowledge test. But the vast majority of those who pass it will go on to become pilots. Remember, the majority of aspiring pilots are not high school or college students accustomed to wading through the semantic rhetorical tap dancing of multiple choice standardized tests, but the businessman or woman who probably hasn't taken a written exam in 20 years. The fear of the written exam was driving them away from reaching their goal of becoming a pilot. So Lucas came up with tricks, techniques, and tools to take the confusion out of the FAA exam and turn it into something simple. Pilot Training Solutions is the result of his ingenuity and passion for teaching.
Okay, some of these questions are pretty much just plain nasty. For example, this one here says, refer to figure 8. What is the effect of a temperature decrease and a pressure altitude increase on the density altitude from 90 degrees Fahrenheit and 1250 feet pressure altitude to 55 degrees What are they even asking? This doesn't make any sense whatsoever. But I'll explain it with a little video and show you how we solve this problem. Pretty much what they're asking you to do is figure out the difference between the two density altitudes. So let's just watch the next couple of slides that are going to show you how to do this using the CX2 and making it really, really, really easy. The easiest way to do this without going nuts is using the CX2 as usual. And what we have to do is calculate the two density altitudes based on the numbers they gave us. So they gave us one pressure altitude at 1250 feet, and the temperature would have been at 90 degrees Fahrenheit. And the next altitude is 1750 with 55 degrees Fahrenheit. So as usual, the first thing we need to do is convert those Fahrenheits to centigrade. So I'm going to put 90 in here, 90, and I'm going to put second, convert from centigrade to Fahrenheit, and I got 32.2. I'm going to write this down, and I'm going to go to the next one. The next one was 55, and again I convert that to Fahrenheit, and I got I'd say 12.8. It was closer. So 12.8, and so I got my two. I wrote these two numbers down. Now I'm going to go to flight. I'm going to go to altitude. I'm going to go to density altitude because we already have the two pressure altitudes, right? So I go to density pressure altitude, insert it in there. The first pressure altitude was 1250. So I'm going to put 1250 in there. Enter. I'm going to put the temperature, which was 32.2. 0.2. Enter. And there we go. I'm going to write down my first altitude, which was 3889. Now I'm going to calculate the second density altitude. So I can just click on clear and put the new altitude. The second altitude was 1750. So I put 1750 in there. I press enter. The temperature was, I believe, 12.8. 12.8 in there. Enter. And I've got an altitude of 1900. Now I can just go back on my calculator. So flight back, calculator 5. And on there, I'm just going to do 3489, which was my first density altitude that I found, minus 1900, the second one, equals about 1600 feet. So the first number was 3489, and we took out 1900, and the difference was 1589. So it's a decrease of 1589 feet, a decrease of 1600 feet. We go back and look at the answers, we can see that 1700 decrease is our closer, answer B. Answer B was our correct. Okay, how exactly do we figure out our position relative to a VOR? As I said at the beginning, I'm going to have to ask you to forget everything you know about a VOR. Trust me, this system is so much simpler than what you're used to. Think about it. The needle points to the right, you go to the right. The needle goes to the left, you go to the left. Oh wait, but you might be in reverse sensing. That's if the flag has a from instead of a to. Come on, this is complete nonsense. How does a VOR work? It's very simple. Let's say that I ask you, what is your position relative to me? And let's say I'm in Texas and you're in Maine. Well, your simplest answer would be to say that you are northeast of me. Well, that's exactly what a VOR does. For example, this VOR is telling me that it is located to the plane, especially if you're using instruments, is probably because you're lost or you're in bad weather. So doing math in those conditions are going to set you even more behind the airplane. So how do we solve this? The first thing you need to do is draw out a heading indicator with a heading of 320 on top. Or again, you could just use our CD and rotate the CD until you have the correct heading on top, the heading given by the question. Second, we're going to move the needle from inside the ADF card into the heading indicator. We have created an RMI this way. So now, wherever the needle points to inside your heading indicator is your magnetic bearing to the station. So in the case here, if as they're asking the magnetic bearing to the station, I can clearly see without doing any math that I have to fly 185 to go to the station. So B is my correct answer. If they had asked me what is the magnetic bearing from the station, well then again I pick the tail and I can see that it's about 015. And yet another enemy for pilots, fog. Fog is a surface-based cloud comprised either of water droplets or ice crystals. It is the most frequent cause of surface visibility below 3 miles and is one of the most common and persistent weather hazards encountered in aviation. The reason it is so dangerous is because it can form so rapidly. And a lot of times you can go from VFR to less than 1 mile visibility in just a few minutes. Fog is most likely to form in coastal areas because of the high moisture content, but it can form anywhere. Fog also occurs frequently in industrial areas due to an abundance of condensation nuclei from combustion products, so pollution. This is a test question. They will ask you, why does fog develop a lot in industrial areas? And it's because of the abundance of condensation nuclei. Remember that, as it will help you on the test. Most students find it really difficult to understand the subtle differences between fogs. So we're going to change that and explain it to you so it becomes really easy for you to understand which fog is which. For example, what distinguishes most fogs is whether the fog was created because of wind, was there a wind factor involved in this fog or not. Radiation fog does not require any wind whatsoever. It's normal fog. It is high pressure going to low pressure, cold air overtaking hot air. The most frequent type of radiation fog is that seen on a clear, relatively still night where pretty much the sun goes down and we have a high moisture content, maybe a lake or some kind of body of water was just very humid that day. And what happens is now Earth is warm and the air surrounding it is cooled. Air cools quickly, but Earth maintains its heat. So what happens is that moist, hot air that is over the ground now becomes cooled down to its dew point, forming fog. So as I already said, for this fog, there is no need for a wind component. Advection fog, on the other hand, would be physically impossible without a wind condition. Why do I say this? Well, because advection fog forms when moist air moves over colder ground or water, which is also your test question. Now, why am I saying that this is impossible? Well, think about it. Warm air moves over colder air. Well, warm air is a low pressure and cold air is a high pressure. High goes to low. But in this case, the opposite is happening, which is physically impossible unless there is a wind condition. So, for radiation fog, no wind. Advection fog, there's got to be wind. That is your key in remembering the differences between these two kind of fogs. And wind is obviously another factor that contributes to performance of an airplane. We like to have headwinds. If you think about it, let's say for example that your airplane takeoff speed is 55 knots. If the wind was straight down the runway and you took off into that wind, you only have to bring the airplane to 5 knots because 50 is already given by the headwind. So your airspeed indicator is actually already indicating 50. So 5 knots is all you require to be actually able to lift off. Now, as usual, the FAA will give you a bunch of questions regarding this, and they will give you figures that you can go to. It's figure 37 in general, the one that I just placed here. And then they will give you questions saying, refer to figure 37, what is the crosswind component for the landing on runway 18 if the tower reports that the wind is 220 at 30 knots. Okay, the way we solve this is, first of all, we need to find out how many degrees it is, and obviously between 180 and 220 there is 40 degrees. So I draw a line down from the 40-degree line until I intersect the wind of 30 knots. Once I touch the wind at 30 knots, now I want, what was the question asking? Crosswind component. Okay, so I want to find out the crosswind component, so I bring a line straight down from there, and again, I find an answer that looks to be close to about 19, so A would be the answer, I would assume, and it is the correct answer. But you know, it's precision is important here. Or again, we could use the CX2. Let's see how do we do that. And again, for the purposes of practice, I'm going to have you do this question. Okay, the first thing you need to do is we need to get into the flight. So click on flight. Now that we've got flight, the crosswind component on the CX2 is found under actual leg. Now that we are in the actual leg, we're going to press 4 for the... Now here we have our wind direction, wind speed, and the runway. Okay, so it's pretty straightforward. First of all, we're going to 2 and 0. Press enter. Now we want the wind speed. That's 30. Now we want the runway, and we can click here. Look at that crosswind component. We've got 19.3 knots, exactly what we found with the other complicated. Well, no, it's really not complicated, but the problem is that if you use the figures, some of those are so small that you end up making a small mistake aligning the line a little bit to the left or a little bit to the right. And as you see, the answers are pretty close. The CX2 guarantees that you will get the correct answer. And nobody does flight planning the old way anymore. Nobody even does flight planning anymore. You have to learn how to do it because, I don't know why, but I guess just you have to learn how to do it. But I'm going to close the statement at that. But the reality of it is there's so much software out there that does this for you, and it's a lot more precise than what you can come up with. So there's no reason for you to do all of this. And again, you are able to use these aids during the test. So, well, no, but I want to do it the old way. Doing it the old way, you might be really good at everything, but still, if you misalign something by a quarter of an inch or less, a tenth of an inch, you will probably get the wrong answer. You will find 23 knots instead of 19 knots. You use a CX2, you can't get the wrong answer. It's that simple. The northeast of me. How do I know it? It's incredibly simple. A VOR, like you before giving me two cardinal directions to get to you, is giving me a couple of cardinal directions telling me where it's located. In this case, the VOR is telling me that it's north and east of me. How do I know this? Well, first of all, that little to from flag, let's just call it a flag and forget that there is a to from on it. It's just a flag. It's one of the indicators that directs you towards the VOR. In this case, as you see, it is pointing down. So I look at a cardinal direction on the same side that that flag is pointing to. If I go straight down from that flag, I can see that it's saying, hey, go north. That is one of the two cardinal directions that we must use to go to that station. The second cardinal direction is shown by the needle. The needle will swing to one side. You must find a number on that side, and in this case it's evident that east is on that side. So I found one cardinal direction for the flag, north, the other one for the needle, east. This VOR is telling me it's northeast of me. It is that simple. Now I'm going to give you another thorough explanation on how we use this method so everything gets clear. Remember, you need to forget what you know. First of all, do you see that to from flag? Do you see the to and the from on that instrument? No, you don't. That to and from does not exist, okay? That's the first step you need to do. Realize that there is no to from. Second, we look at what side the flag is pointing to. As you see, the flag is pointing straight up. This pretty much means that the cardinal direction it's pointing to will be on the top side of the instrument. The bottom 180 degree of the instrument you can pretty much black out because our cardinal direction cannot belong in the bottom side of the instrument. Now, straight from the top, if we look for a cardinal direction, the closest cardinal direction to the top of the instrument is what? We have west on that side and south on that side, but the closest cardinal direction to me is south. That's one of the cardinal directions. We need to go south to get to the station. Okay, south is one of the two cardinal directions we are required to fly to get to that station. Fourth, now we're going to look at the needle. Okay, now we're looking at the needle, and the needle is on the left side. This eliminates the right 180 degree side of the instrument, meaning our cardinal direction, the second cardinal direction that we're looking for, cannot be on that side there, and that's why it's gone. The cardinal direction is on the left side. If I go straight to the middle of that and find the closest cardinal direction to the middle, as you see, east is on that side. If we want to fly to the station, we need to fly south and east, putting us northwest of the station. Okay, this one here is incredibly easy. It says, refer to figure 27, areas 4 and 2, and figure 29. The VR is tuned to Jamestown VOR, and the aircraft is positioned over Cooperstown's airport. Which VR indication is correct? 1, 4, or 6? Well, you can see from the figure that Cooperstown Airport is obviously to the northeast of the VOR. As shown by this line, you would have to fly southwest to get to it. But let's not even put the west part. Let's just put we know that we have to fly south. So look at VR number 1 and VR number 4. Do you see those flags? They're pointing straight up. If we look for that cardinal direction, it's north in both cases. Well, if you fly north from Cooperstown, if you have enough gas to circle the world, eventually you'll get to the VOR. You're going for the North Pole, and yeah, probably not a good idea. So you have to fly south. C, number 6, if you look at that flag now, that flag is actually pointing down. What's down there? South. And actually, because the FAA still uses these antique drawings, and I take them directly from the FAA, so you will be familiar with these figures when you take the test. But because these are old style VORs, you can't actually see the numbers at the bottom of that instrument. So I'm telling you that south is there, north is there, west is there, whatever it is, but you can actually see it. South is there. What you can do is use a little trick handy with what we gave you. Well, the CD that we gave you, the cover of the painting on top of the CD is done on purpose. It's a heading indicator, right? So you've installed the program on your computer. Now take out the CD, put it back in the case, and turn it around as if it was a heading indicator. So now if you put those numbers on top, you can see that at the bottom where the flag would be pointing, south is there. Now for a little bit of a more complicated question. The question says, refer to figure 31, illustration 4. On a magnetic heading of 320, the magnetic bearing to the station is, and those are your 3 answers. The easiest way to do this, I know they've taught you that there is a formula, magnetic heading plus relative bearing equals magnetic bearing, but nobody wants to do math in an